Cool. Well, thanks for coming. Today I want to talk about backdoors in JavaScript and in particular in crypto systems. I work for a Bitcoin wallet company, and a lot of our wallets are written in JavaScript, the front end stuff. The reason for that is we want you to be able to control your own private keys, control your own funds. So that means your device has to be able to generate this random data. We don't want it. We don't ever want to hold that. You can back it up to us by encrypting it with your password or whatever, but we don't want your private keys. So the way you do that in the browser is with JavaScript. So one of the threats related to this is that we have this deep stack of dependencies. We have the developers that work for us. Some companies also accept open source pull requests to GitHub and stuff like that. And practically anywhere in that whole stack of code, this massive pile of code, someone could insert a single line in there that steals everyone's private keys. It's a big problem. It's a big challenge. So today I want to talk about what that might look like if someone did this and start talking about how we can be on the lookout for it, some techniques we can use to mitigate the effects if there is underhanded code in our systems. So JavaScript has lots of good things going on for it and has a few downsides as it applies to security and doing crypto in particular. For years, people were saying, don't do crypto in JavaScript. That's insane. You got to do it in C++ or some strongly typed thing. You can't just be running code willy-nilly, switching between types for your variables. It's going to explode. And they're kind of right, but we're managing OK so far. So JavaScript on the plus side is web ready. It's very quick to develop. You can come up with your prototype and get it to production quite fast. Lots of great libraries to use. It's being used now for crypto by things like password managers. If any LastPass users in the audience? A couple, OK. I like LastPass. Bitcoin wallet, of course. It's open source friendly, but JavaScript is also very, very easy to obfuscate and to sabotage. So we're going to talk about how to make that not happen. Or, if you're an evil person in the audience, I guess you could be taking notes too. So since we're going to talk about, so a lot of this is going to be a carryover to general JavaScript for sure, but I'm particularly interested in crypto code. So I want to take a moment talk about what we are going to expect if we're looking at crypto code. This screen is very small, so you're gonna struggle to see all of the stuff going on with the code. But I will narrate for you. And just so you know, all of the material that I'm basing this on, I've put it into a single GitHub repo. And I'm going to put the slides up online too. So if you're interested in this stuff, you want to take a closer look, it will be on GitHub. So here's a little excerpt from the Crypto.js node library. And this is part of their excerpt of AES. And some things you're going to notice that you're going to see over and over again in crypto code in particular, cryptographic implementations. We have lots of loops. So we have like a for loop here. That's because crypto code tends to operate on chunks or blocks of data one at a time. You see lots of magic numbers. These are very fuzzy right here, but there's some magic numbers. And these are going to generally either mean that they are the magic numbers that are from crypto, the cryptographers that came up with them, that somehow through their mathematical magic figured out that these are useful numbers for obfuscating things and making it hard to decrypt things without the key. Or it may mean that there may also be numbers that pertain to selecting little chunks of memory of data at a time and operating on them piecewise. Along that lines, you're also going to see a lot of arithmetic in crypto code, which you may not see a lot in JavaScript, right? If you're writing some front end for a website or whatever, there's probably not a lot of bitwise arithmetic that you're using in that. But you definitely will see it in crypto for sure. And you wouldn't see it in these excerpts, but other things you're going to see are like encoding, decoding functions. A lot of, for example, if you need to be able to handle lots of different kinds of data, like Unicode encoded data, for example. And padding is another big thing. It all has to do with standardizing data so that you're operating on it in a deterministic fashion. So one person's AES function works the same as the next person's. So here's the first example that I want to talk about. We're going to go through some code examples, and I'm going to talk you through it since you won't be able to see this tiny text. So this example is the go-to fail bug that came up in the last year or so. And this was a bug in the iOS operating system. I actually pulled down the C++ excerpt. And so what you have here is you have a series of, it's doing some kind of validation of the certificate. And you have a series of checks here. If this happens and there's an error, go to fail. If this happens and there's an error, go to fail. It does that over and over. And you finally get to this line right here. And if you were not expecting it, you may not notice this. And unfortunately, a lot of people did not notice it. But if you look very closely, this section right here is a little asymmetric. You know, there's like one line, one line, one line, one line. And then there's two go-to fails here. And the problem here is that actually this go-to fail has absolutely nothing to do with this if statement. So if you get down to this part of execution, you get to this line, it always goes to fail. And this resulted in some horrible memory disclosure bug or whatever. And everyone's phones were vulnerable, and it was a big disaster. Now, if they had bothered to put this code through a linter, a linter is like a kind of compiler that has some very specific expectations about how code should look, and it complains when the code doesn't look that way. If they had bothered to do that, this absolutely would have come up, right? This does not pass the sniff test for a linter. And so I actually think that linters are a good place to start in terms of figuring out like how the hell would we detect underhanded code. The thing I really like about this example is that it's such a small, simple error. You could easily imagine that someone made this by accident, or that they did it in they thought about this a tremendous amount and thought very carefully about how to insert it in there. And as a philosophical experiment, I think it's interesting to think about, like, if someone's inserting underhanded code into a code base, do they want plausible deniability? If they do, then they're much constricted in the kinds of bugs that they can insert there, right? Because if someone knows who they are, what they wrote it, right, and they find the bug, it's the 0 day, everything blows up, right? And they're like, Dave, what's up with this extra line that you inserted there, right? You might go to jail. So it's really interesting to think about like attackers who first don't want plausible deniability. Maybe they stole the Bitcoins, they've gone off to the Cayman Islands, they're gone, like you can't find them, right? Where's Dave? Well, he didn't come into work today, right? Or maybe they do need plausible deniability after the fact. So I rewrote this in JavaScript, and it looks kind of similar. There's no go-to labels in JavaScript. Actually, there is a person that implemented them, but it's very evil. It involves eval, and don't do it. So similar kind of shape, right? Now, if you pass it through JSLint, which is a popular linter program for JavaScript, in order to get it to stop complaining, you can't have this kind of shape to the code anymore. You can see you have a bunch of if, then fail statements right here, and then you have this guy off here, not indented, sitting off there by himself, and it's much easier to spot. So I think linter is a good place to start for this stuff. I participated in a contest a few months ago that they held online. It was a Java misdirection contest where we tried to do this kind of stuff on purpose, and we tried to do it in some clever way. I'm going to go through a couple of these examples just to show you, how smart people who are doing this contest would go about doing these kind of techniques, just to give you like a sample of how it might be done. So the point of the contest, the prompt for it was, okay, yeah, you're going to have a browser, little browser app. The user is going to type in some nonsense in a text box, and it's going to be sent to a generate key function that you write in JavaScript. And what your generate key function is supposed to do is it's supposed to take the input and give back a private key, a secret key to the user using broken crafted crypto if you want to. It's not about whether it's cryptographically like strong or not. But in the process, we want you to cleverly exfiltrate this key to some remote location in the process. Okay. So what I did for my example, I used CRC32, which is not a secure hash function. Don't use it for security things, but it's very, very short in its implementation. And as you can see, I'm running this in JSFiddle. Great website, JSFiddle. People know that JSFiddle. And so the user typed in some characters. It shows back the key here. And then I also have the network developer tool open in here in Chrome. And you can kind of see blurrily there's a bunch of network traffic that's being created as a result of the user typing into the text box. That's not supposed to happen. And so actually, the requests are going to newval a bunch of digits.mydomain.com. Kind of suspicious. So if we start to look through the code, I'm going to narrate this for you again. So there's a few main functions here. There's not depicted as the generate key function. All that simply does is it just sends it to the crc32 function and then gets the result back and fills that in for the user and the DOM. So we also have a UTF-8 encode function. That doesn't do anything tricky. It just does what it's supposed to do. We have a getDomain function here. And we have the crc32 function, most of which is an honest implementation of crc32. It really does what it's supposed to do. This code block right here, however, does something curious, right? So if you were reading through the code, what you would see is I have a little comment there, and it's like, oh, this is a sanity check. Okay, so there's a value here that's part of the key that we're computing, the hash that we're computing, called new val. What if new val, for some crazy reason, right? What if it was exceeded math.max or it exceeded math.min? Well, that would be bad. Like, we wouldn't know exactly what would come out of this function anymore. So yeah, just a little sanity check. This should be very rarely displayed. And the following lines say, if that happens, what we're going to do is we're just going to show a warning image to the user, right? So in the freak accident that this thing gets displayed, we're going to show them we're going to load it from mydomain.com, and it's going to be a warning and say, your private key is compromised. Please refresh the page or whatever it is. Don't use this for your cryptocurrency transactions. And so it calls, it's building the URL, and it calls this getDomain function. And getDomain, it has this thing where it's like, oh, well, we're going to take a parameter. We're going to log that parameter to the console just in case an advanced user wants to see what's going on here. And then we're going to return the domain at which the image is loaded in. So if you're reading through it, it kind of looks like, okay, it's going to return image.mydomain.com/warning.png. It loads this into an image in the DOM, right, and then it displays it to the user. And this is just like a freak thing, only if the sanity check is run. Now there's a couple problems with this that I purposely created. The first one is that this variable up here is called var arguments. Does anyone know anything about arguments in JavaScript, the keyword arguments? So arguments is actually a special reserved keyword in JavaScript. When you refer to it as an array in JavaScript, it refers to the parameters of the function, right? So here and here in these two functions, when I refer to arguments 0, which I pretended was some global array, it's actually not referring to that whatsoever, but it's referring to the parameters to this particular function. A little bit sneaky. So now that you know that, you actually see, well, the thing that's being logged is actually getting inserted into the URL. So instead of loading image.mydomain.com, it's like the private key that we're not supposed to leak .mydomain.com. And that's not so great. Okay. But you might say, well, but it's just a sanity check, right? How could that value ever be higher than math.max or lower than math.min? Well, I've done another thing here where, for some reason, you might consider very sloppy, but plausibly sloppy. Instead of comparing it to math.min, I did math.min parse float, which, due to the unique quirks of JavaScript, turns into infinity. And so the value is always less than infinity. And so that if condition statement block is always going to be executed every time. So the user, they type in their numbers. It always executes this block where it loads this image that doesn't actually exist, and it's exfiltrating the user's private key to this subdomain. And you can easily set up your web server and DNS crap so that it will capture this, right? So I just want to give you that as sort of a taste of how people might go about doing this. And this use of images is a popular thing for security professionals in JavaScript. We also use images to do things with cross-site scripting, proof of concept exploits, and all kind of stuff. So images are a popular way of I'm going to make the browser make this HTTP request, and it has to wait until it gets the request back to find out, oops, it wasn't actually an image. It just accidentally leaked some data. Now, if we pass that into JSLint, it's going to immediately throw up a few important complaints, right? And they all revolve around that use of the word arguments. So four error messages here, and it says, first one, I expected an identifier, but said I saw this keyword, reserved keyword arguments. Don't do that. And as soon as you resolve this in the code, it completely breaks the exploit, right? So that's great. OK, JS Lint would have saved us. Likewise, it's complaining about the reference to argument 0 in the functions that I wrote. You can't assign to it, et cetera, right? So it doesn't like any of this. Now, JavaScript will happily run all of this code. It won't do anything about it, even if you use strict or all that kind of stuff. But JS Lint picked it up. Great. Fantastic. All right. I'm also going to very briefly go through this example as well. This was another submission that someone made. It's very short, and this was actually the winner of the competition. The one reason that I don't like this submission is that it is obviously janky, right? There's some weird shit going on here. There's a hex encoded string here. It's being called to a bunch of new function stuff. You have a bunch of like weird hex encoded numbers mixed with mat.random. OK, that's kind of. But then you have this absurd for loop that just does like it's obviously obscured JavaScript. So just talking you through what's happening here, just to see like how much stuff you can get done in just a few lines of code, right? So that just the first 2 lines of code are amazing. First thing it does, this hex string is actually equal to the string image. Then that gets implicitly cast from a string into an object. Now it's an image in the DOM. The seed argument actually it uses the payload parameter argument that was passed from the user, or the user typed something in. That's the payload. It passes it to math.random. This is the only place where that gets used. But math.random doesn't take any arguments, so it just gets ignored completely. So like if you're looking through the code and you notice that the only place where it's supposed to be the seed for this random number is being completely ignored, like that's obviously a little odd. If you take the value that you get from math.random, it's between 0 and 1. It's a decimal. You XOR it with some hex thing. You get the same number back. There you use this weird character, which is a tilde character, which takes the number, it adds 1 to it, and then multiplies by -1. Why you would need this built into the language, I have no idea. And so like once you unravel all of that stuff, actually the second variable is equal to the string src, or source, right? So if we see anywhere in the code hasher.seed, it's equivalent to image.source. Interesting. And in fact, down here at the bottom here, we do have a reference to the seed as being sort of a field within hasher. I'm not going to go through the whole for loop, but the end result is that it builds up the string. The for loop is also amazing, but it's very complicated. So it builds up the string. It has the random digits that it generated from math.random.src.sr. And it then sort of makes that part of the DOM the actual image. So it loads the image, or tries to, and it returns just the string part to the user using the slice function. And what's cool about this is that .sr is the TLD for the African Republic of Suriname, right? So it could be a real website that they're exfiltrating this data out to. And so really just got a lot of clever stuff going on there in a short period of time. And I think it gives you an idea of like, oh my God, there's so many things that can go wrong in like just a small amount of code. This is not lint friendly at all. If you try to pass it into lint, it will just explode, right? So you'd have to make a lot of changes to this to get it through lint. I'm not sure how viable that would be. This example is super cool. This is done by a guy named F.E. Gabaye. And you can see this here a little bit because I blew it up a little bit more. But what I want to summarize for you what this does. So in JS Fiddle, you have this pane. So you have your HTML code, you have your CSS code, you have your JavaScript, and you have a result pane where it's rendered and it runs the code, and you can interact with it and stuff like that. That's the result pane. So the way that JS Fiddle does that is it actually it renders it as injecting it into this div called result, and it puts the body there in an iframe, and then it takes the code block and puts it down, slaps that down underneath the HTML. Now, what he did was he used this function, which doesn't seem obviously concerning. It's called next element sibling, which basically means when this is being referred, when this is being injected into the DOM, when we're looking at this stuff, well, the next sibling is actually this script block. Now he has this comment, this innocent-looking comment at the very end of the thing that says, coded by Effie Gabbay. My blog is fun. You can find it at http://www.hex.254.com. Oh, fun, you know, Effie's a good guy. It's so nice of him to write this code for us. Well, actually, he manages to use a regex that just finds the link part of this, and it takes the private key and leaks it to a URL under that domain, right? I just thought this was so clever, like putting the link where you're going to exfiltrate the data to in a comment in the code and referring to it based on where it is in the DOM relation to it was just like super clever. I was really impressed by that. I'll mention very briefly this example. So the one thing that I want to point your attention to here is there's a variable called salt. And the string here is // and then a bunch of digits, and then another couple of slashes. And it just says, oh, and then I added this comment in here. So what that is, it's an alternative representation of 127.0.0.1. And there's a bunch of ways that you can represent domains, IP addresses, and stuff like that. If you look up like representations of IP addresses, like a bunch of weird-ass ways that you can do it. And when you talk about IPv6, it gets even more bizarre, right? So just be aware that if you're trying to look through some code and you want to, like, all right, well, I'm going to be on the lookout for references to weird, janky domains that I've never seen before, you have to be prepared to know all the different kinds of representations that you might see this stuff in code. And JavaScript is great at being able to decode things, either through implicit casting or obscure little functions or whatever, make it very difficult, just if you're just reading through the code, to anticipate how things are going to be transformed from their original state. This is the last example from the contest that I want to go through. And this was done by a guy named Evan. What I really like about this example is that it's very plausible looking at first. It's not like the winning example where it was like a clearly obscure JavaScript. You have this array up here that generates it's some kind of veneer key. Okay, veneer cipher, fine. And then you have some stuff that looks like, okay, yeah, it appears to be taking the input from the user and like somehow like XORing it or doing something with the veneer key, combining it in some way. It does that for all of them, and then it returns it back to the user. OK, great. Like, it's very plausible looking when you first look at it. But there's a couple of subtle things that are happening here. The first one is, in this for loop, you have for I equals 0, I up less than or equal to input.length, I plus plus, basically. Now, does anyone know offhand what the problem is there? Well, if you're going through an array, you do not. Right, exactly. When you're going through an array of something, you do not want to, you want to do less than, because you want to go up to the last item, which is the index is equal to the length minus 1, right? It's a 0-based array. If you do less than or equals to, the last item that you pull out of the array is going to be some null value. JavaScript doesn't choke on that. It's just like, meh, OK, let's see what happens, right? It's a very like YOLO kind of language. And so what happens then is, instead of combining it with the input, on that iteration of the for loop, it actually takes this whole thing, which if you were going to decode it, is a bunch of ASCII values that decode to a hidden iframe that then exfiltrates the data. Okay. So what I really liked about that is that it's very plausible. The other scary thing about this is that it's completely lint-proof. Lint is very happy with this code. I cleaned it up a little bit from its original state, but it's happy with its code. The exploit still works. So that should teach us, like, we can't just rely on lint to identify this kind of stuff. OK, there's 2 more examples that I want to talk about, which I find very, very cool. This one's from Bitcoin. So it was originally in C++, but I've ported it over to JavaScript because it works just as well there. So this refers to what in Bitcoin we have these Bitcoin improvement proposals, which are like little documents that say, like, well, here's this problem at Bitcoin, here's how we propose to fix it, et cetera. Similar to what Python does and some other languages. And Bit42 talks about the fact that there was an integer overflow in a very important, but important in the distant future, function in Bitcoin, where when you calculate the subsidy that is returned to a miner when they mine the block, there was an integer overflow with it. So in Bitcoin, when we first launched the blockchain, it was supposed to be 50 BTC that you get for each block. And that's supposed to be halved every 4 years until it gets to 0. And at that point, it just stays at 0 forever, right? That's how we know the supply curve of the currency in advance. Well, what happened here was because of the integer overflow of the int64t type of integer, the 64-bit integer. So when we hit block 13,444,000, it would wrap over and it would start giving back 50 BTC again, and this would happen for infinity. Now this is not like a very severe problem, right? Because this is like in the way, 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 way distant future. But we figured, probably better to fix this now, just to be on the, just to make it clear that we're doing things robustly, right? And so this would repeat every 210,000 times 64 blocks. Now, when you fix it, and if you go on GitHub, you'll see, or if you look at the slides later on. So I have the broken version and the fixed version, which I pulled down from the Bitcoin core code, and it's in C++. Okay, and the fixed version, once it hits 0 BTC, it just stays there. Great. Okay, so I ported this over to JavaScript, and it turns out JavaScript still also has integer overflows of various kinds, right? And this is another possible disaster area where the arithmetic in JavaScript can have very unpredictable results, or maybe potentially undefined results. So you have to be very careful about that. So what happened in the JavaScript version, if you just take the broken version, very similar thing. Every many blocks, it wraps back over to 50 BTC. If you literally ported over the fix, it would have a similar problem where just once it would wrap back to 50 BTC, but it would not do that indefinitely. And the reason is because one of the integers that's involved is a 32-bit integer rather than a 64-bit integer that's in C++ in the C++ code. Okay. Now, there's two ways that we could try to tackle this in JavaScript, this general problem. One is we could try to throw some errors when we know that the values are not looking so good, right? So what we really need to do when we have an operator in JavaScript that is complicated in some fashion, I would encourage this to happen for every mathematical operator, like plus, minus, et cetera. Go look in the original ECMA script definition of what this operator does, figure out what the maximum and minimum values that it can handle, and then check in your code if condition comes up. And if it does, then you throw an error, right? And this is not something that uses up a lot of CPU cycles or anything like that. This is like, this is pretty easy to do. Adds a few lines to the code, but fine. Now what would happen here is we would get to that certain block, and it would overflow, and then we'd throw an error. Now you wouldn't actually want to do that in Bitcoin, right? Because what would happen is we'd get to that point in the future, and then the entire network would just crash. You'd never be able to mine any more blocks because it threw up this error, right? So you'd want to handle it a little bit more gracefully. The other option is to use classes, libraries that can handle very big numbers. So Node.js has a big integer class. So if we just make all of our variables that are handling this stuff big integer classes, well, they operate on arbitrarily large numbers. And actually, there was one number that I figured it's a right shift bitwise operator, and that can only handle numbers up to some like astronomically large number, at which point it rolls over and becomes infinity. So you could check for that condition. But overall, this is a much cleaner, much better way to handle that kind of problem. So when we're looking at these kind of arithmetic problems in the code, and arithmetic problems can come up inadvertently. I'm sure this wasn't inadvertent. Like this was written. The problem that occurred, the code was originally written by Satoshi. I'm sure he didn't think he was going to go like 500 years into the future and like somehow exploit this, right? So these can happen inadvertently, but they could be underhanded code too. So like you have to like review arithmetic very, very carefully in JavaScript. I would really encourage you to refer back to the original spec for ECMA script, which changes every year because they're doing that now. And just, be aware of arithmetic. I think there's some other helpful strategies that you could adopt. One is like before you deploy the code, test some boundary conditions. This may be part of your unit tests that you want to look for extreme values. And you want to define explicitly what's supposed to happen in your code when it hits one of those extreme values. Don't just like, don't just like half-ass it and say, well, it's going to throw up an error or whatever, right? And I also would say, it does dirty up the code a little bit to do this, but I'm in favor of checking pathological conditions during the execution of the code, right? And finding a way to fail gracefully. Even if you think that these scenarios that seem a bit implausible at first, I would really recommend that's a good idea. But I'm a security engineer, so I'm sure the developers in the audience will hate me for that. So, OK, one more example that I want to go through, and this is a great one. This has to do with attacking compilers of JavaScript. So in JavaScript, people love compilers. They want to minify their code. They want to compress it. They want to write it in one JavaScript-like language and translate it over back to JavaScript because CoffeeScript is so much better, bro. And so we have a lot of compilers. And there's a security researcher. Her name is Jan. She goes by bcrypt on Twitter. She's super smart, cool lady. And she had this idea. Someone had written in a security magazine called POC. They were talking about this in a general idea of like attacking compilers, finding bugs in compilers so that the code would run differently before and after you've put it through the compiler, right? Abusing the way that compilers change the code so that they end up doing something different from what's originally intended. So she did this for JavaScript, and she attacked the uglify.js library, which is used very widely. She went through the Git repo and found an issue on GitHub for version 2.4.23, which relates to De Morgan's law. And she came up with this little authorization, like a sample authorization script, and showed. We'll get to it in a moment. So De Morgan's law, anyone, De Morgan's law? People are familiar with De Morgan's law, CS class, many years ago maybe. All right, so De Morgan's law is like, it's a law of mathematical logic or bitwise arithmetic, right? So if you had the expression not A and not B and not C and not D, you could move the nots out to the outside, and then all of the ands turned into or. So a not, and then A, B, or C, or D, A or B or C or D, right? And minifiers actually like to use this because they can save a little bit of space. These two expressions in JavaScript, they go from 14 characters to 13 characters. OK, all right, it's a legit minification, not huge subsidies, but not bad. Now, this raises the question, though, because JavaScript has this notion of truthiness, right? Lots of the things that we think are going to be Boolean values turn out to be something other than Boolean values. For example, the number 0, if you evaluate in JavaScript in a Boolean context, it will just turn it into false. OK, all right. And numbers 1 through whatever turn out to be true. But what if a minifier was confronted by this, right? And it's expecting to apply De Morgan's law to a bunch of Booleans, but there's something in that expression that's not Boolean. It's being implicitly cast to a Boolean by JavaScript. Well, then things go wrong, right? So here's the example that she came up with. This is just a very simple example. So we have like a user class, some kind of config thing, OK, whatever. Get system time, gets the system time. The user class has a token, and the token is either invalidated or it's not, and it has an integer that says when it's going to expire in the future, right? And we have this function over here that says, OK, how much time between now and when it's expired, so we can figure out whether we should authorize the user or not. So we have this function here that does the authorization check, and it's written a little bit weirdly, just to make it clear about like De Morgan's law and blah blah blah, right? She didn't spend a lot of time trying to make it like super duper plausible. But if you would look at it, you would just say like, well, this person's kind of a dumbass, but like there's nothing wrong with this code necessarily. It's gonna run fine. So the weird part is like, okay, not config and not user token, and then a bunch of other things. The last thing is like, and we want to make sure, so we're checking, does the user exist? Does they have a config file? Does the token exist? Is it invalidated? Is the config file initialized? Blah, blah, blah. All right. And then this last thing is how much time is left until it expires? Now, when we, and then I have like a little bit of stuff here that just shows what it's doing, right? So we're creating a user, and right off the bat, their token is expired. It's 0 until the token is expired. And so it's not a valid user. Oops, and it says if it is valid, say user is valid. If it's not, it says user is not valid. Now we run this through Uglify.js, and actually did this, and you can go on in GitHub and find the instructions how to compile it yourself if you want to compile. Yeah. And this is what happens. So when we run it, before we put it through Uglify.js, this particular version, user is not valid. Great. Put it through Uglify.js, run the minified version. User is valid. Crap. That's not good. So it actually really worked. So I think this is a very interesting way to attack things. The idea of going after a compiler. And there's some strengths and weaknesses that you could think of for the attacker on this, right? So potentially it's very much more targeted, right? Because instead of just going after all of the users of Uglify.js or all of the users of a particular library that we're trying to target, we're trying to find the cross-section of just the people that are using the library that we're attacking and use this particular Uglify.js version, right? That's much more targeted, and that's good for the attacker in some ways because more targeted 0 days are more likely to take longer to find for people, right? If it affects everyone in the world blows up, we find it right away, it's a dead 0-day vulnerability. Now, on the other hand, if the target victim that you're trying to go after changes the compiler version that they use, well, then they've just broken your bug, right? So it's kind of fragile, it breaks quickly. Potentially. As far as deniability goes, I think it's kind of a mixed bag. You could imagine that depending on the sophistication of how the compiler bug works and how it's expressed in the library that you're attacking, maybe you could do it in a way that would be very plausibly deniable. Maybe not. Maybe after people figure out how it's being exploited, they're like, wait a minute, like, Dave, you inserted that in there. Like, there's no good reason for you to do that other than to exploit this compiler bug. You're going to jail. So I think that it's a pretty interesting avenue to think about. OK, wrapping up. So we went through some examples of like how people can be evil. What are the general principles that we can learn from this? Do any of you review peers' code? Do you do peer review for other people's code? Yeah, OK. Do you have a checklist that you go through when you review it? No? I say that you should. You may have like a mental checklist of things like, OK, for this type of code, I'm typically looking for this kind of thing. I think it's a great idea to have an explicit checklist that you go through. And if you did that, here are some of the things that I would add for you that relate to underhanded code if you're looking for that. So number one, does this code that I'm executing, does it execute code from external sources, right? If it's pulling in from external sources, which are not in front of me, that's a potential problem. It's usually suspicious, right? Usually you don't need to do that. Do I understand all the arithmetic that's in this code? Does it pass lint checks? Obviously, lint sometimes is very helpful here. Could this create covert channels for leaking data, right? Does it create an image tag, for example? Are the variable values clear as I'm reading through the code? Do I understand what the values are going to be as I'm going through it, or is it really hard to follow? If it is, maybe it merits a little bit more scrutiny. Are the variable types consistent throughout execution? It drives me absolutely insane when I have to review JavaScript code where the variables keep flipping between different types depending on the context in which they're used. It's terrible. Don't do it. You will drive people like me insane. So you should be on the lookout for that as well, because that's a great way of doing things in an underhanded way. Does the code clearly delineate global and local scope? If you remember in my submission to this contest, one of the things that I played around with was global versus local scope, using this reserved keyword that only refers to local things and not actually ever using this global variable that I created. And the last thing that I would add to the checklist is, have I actually run this code, and have I looked at some of the stuff that it's interacting with, right? Have I looked at the network traffic that it's generating? Have I looked at, if it interacts with a file system? Have I looked at what kind of files it's opening and reading from and writing to? All that kind of good stuff. So it'd be great to have some kind of tool that helps you, that inspects how it is interacting with the different other things in the world that it's interacting with. Other suspicious characteristics. Is the code using weird JavaScript conventions, like a tilde operator? What the hell is a tilde? Magic numbers always merit further inspection, where there's some number in there, and they're like, where did that come from? Go find out where the number came from. That's how you combat that. References to strange IP address or domains. We talked about that before. Unused variables, dead code. Those are both ways of misdirecting the reader and making it hard for them to understand what's going on. There's another, there's so many great submissions for this. There's more on the GitHub repo that I've explained how they've worked. I've sort of reversed them and stuff like that. One of them, which was really good, it had like Unicode variables. And so it had, like the word code in there. And sometimes it had a funny E that looked exactly like E, but like it was like Scandinavian E or something, I don't know. And when you run that through Lint, it will say like, don't do this. Like Unicode variables, no, you can't do this, right? So Lint is your friend there. The use of non-standard or old libraries that may contain intentional security bugs or bugs that we know about, be suspicious of that. Tools that you might want to use. By the way, the dog went from suspicious to so suspicious that he found the go-to fail bug. Oh, good doggy. All right. So Lint Debugging, running the code and debugging it, and running it in a debugger context and like stepping through and see what it's doing as it going through execution. You can insert console.log statements if you want. You can use the debugger statement, which works in browsers now, where it will you insert debugger into it, and in Chrome, for example, it will pop up with this like really sweet debugger, JavaScript debugger, where it's showing you the values of all the different variables as it's running, and you get to step through and all that cool stuff. The old school tool that we used to use is Firebug. Some people are probably still using that in Firefox. I also would recommend using a network inspection proxy of some kind. So those are built into browsers these days. They're not very pretty to look at or very good, I find. Some other ones are Burp Suite, which has a free version, Fiddler, Zap by the OWASP project. And then if you have some kind of protocol that's more like low level or whatever, you may have to use a specialized proxy, or you can use TCP dump or Wireshark or whatever it is, right? But this is like, anytime that you're suspicious of some code, this is like the level of scrutiny that you should be subjecting it to make sure that it's not stealing all the Bitcoins. Other just like basic like defense in depth stuff that you could do to make underhanded code more difficult or less appealing. Accountability, right? If projects are accepting code from people that have reputation, like it's burned if they've introduced a vulnerability into the system, that's a system that's going to be more resistant to underhanded code. Be careful about your dependencies. Make sure they're up to date. If you're running Node and you're not using Snyk.io or one of these other services, start using it, because it tells you when you have old libraries that are sort of included in your code that you need to update. Ideally, we should be reviewing changes that the authors of these libraries are making as we pull them in, not just be like, yeah, I'll take anything that starts with a 1, version 1.anything, and oh, you got a new version, yeah, pull it down. Let's get it in production. I'm not such a fan of that as a security engineer. You could also compare like the libraries that you're pulling down against private repos that you maintain to just make sure there's no tampering involved there. There's a really cool technique that people are mostly not using. They're using it at Dropbox. But I want to point your attention to this paper that was written a few years ago called Privilege Separation for HTML5 Applications. And what they realized was, okay, so we have JavaScript. Like everyone's doing everything in JavaScript now. We have 1 million libraries. We have like 5,000 node dependencies that are all 5 lines long. With we don't want to ever write code ever again. We're just going to do everything with dependencies, right? And people could mess with things could happen anywhere. This is terrible. So we have content security policy. We have some other stuff in the browser that can help with this, but they're not robust. So their idea was well, We do have one tool that's really useful that works quite well, which is the standard same origin policy in browsers that prevents stuff loaded from one domain from interacting with stuff loaded from another domain. And you can put it in an iframe, and you can use the sandbox directive and sort of put them in little jails, right? And so their idea was, well, what if instead of like having a web page where you just load all of the JavaScript into one big thing and we run it all and it all gets access to the entire global scope, and rather than doing that, let's load a framework at the top. And then all of these different little bits of JavaScript that we're using, we're going to load them in little child iframes. And then they're going to only be able to talk to one another through messages sent through the parent. And so everything is like clearly mediated, nothing like tricky going on. This is a really cool framework. I'd love for people to take a closer look at it and consider it as a mitigation strategy. And they found, this may sound like it would be, it would take up a lot more performance, but actually it runs very, very nicely. And they're using it Dropbox. Limited novelty of what you're doing, right? So use standard libraries, particularly for crypto. Don't use like funky new libraries that your friend wrote. And basic AppSec stuff is like, input and output validation and encoding. You can use content security policy as well that can kind of limit, like, okay, someone got some underhanded code into the thing, but maybe because of content security policy, the browsers are going to refuse to like start loading code from his like evil domain or whatever. That's a way that you can kind of mitigate the effects of this stuff. Briefly, some like references and resources that you may be interested in. I'm not going to talk through all of them, but I'm going to put this up on GitHub, and you can check them out. There's a bunch of contests for underhanded stuff, which I find fascinating. So I'd encourage you to check them out. Someone wrote a book about how to be a complete arsehole on this stuff. If you Google for WTF.js, it tells you about like all the weird quirks that JavaScript has that you should be on the lookout if you're a reviewer of JavaScript code. And some of the stuff that I referred to, the JavaScript misdirection contest by Peter Jarek, the GoToFailBug, and Jan Decrypt's work on attacking minifiers in JavaScript. So if you want to get in touch with me, Twitter, Kristov Atlas. On Twitter, KristovAtlas.com is my blog. All of this stuff all the materials for this are online at GitHub, Kristov Atlas, underhanded/JS/crypto, or just tweet at me and be like, yo, bro, where's the link? And also, I work for the Open Bitcoin Privacy Project. We do all of their stuff, all of our stuff in the open, since it's the All Things Open conference. I just thought I'd mention that. You can check that out as well. And by the way, thanks Blockchain for sending me here. I really appreciate that. It's my full-time employer. We're hiring. We're looking for UX designers, DevOps system engineers, internships, marketing people, all kinds of stuff. So if you're interested in working in the Bitcoin space or the cryptocurrency space or the blockchain space, come hit us up. You can send me an email at kristov@blockchain.com. And if this sounds like a good idea to you, but you're like, this guy's a douche. I work in New York City, and there's also a London office. So just be aware that's a possibility as well. So that's it. Thanks very much. Do you have any questions before you mosey on into the night? No pressure.
Have you seen any language level JavaScript sandboxing attempts?
Language level. Yes. Okay, so I'll mention two things there. One is like there are some frameworks like Angular, for example, where they have some sandboxing that they do. It's not very robust, right? People keep breaking it every once in a while, and then they put out a new version. And I think they're planning to get rid of the sandbox in the future, which my coworkers are going to be very sad about. So that's a thing. People also sometimes try to play with like, okay, well, if I keep this stuff out of global scope, and like if I try to scope things so that the code that I do trust is in a different like context than the stuff that I don't trust. There's some playing around that you can do there, but I'm always like afraid that some very clever JavaScript coder is going to find a way to like jump into the context that I thought he couldn't get into. So I'm a little bit iffy about that stuff. Anyone else? Yes.
How does this differ from, say, you have the browser security model?
Yeah.
Having the same applications being deployed in, say, the Electron environment, right?
Mm-hmm.
What changes about the security model when you shift from the browser to Electron?
So remind me a little bit about how Electron works before I.
Just the WebKit from the shell without all the browser features, right?
Right. I think it's going to be pretty damn similar. You could probably think of Electron as being sort of like its own browser, and each browser has its own quirks in terms of how much it tries to sandbox things and like the little details of how it handles same origin policy and all that kind of stuff. But yeah, there's like a lot of apps being built off of Electron and like similar things like that. And I think they're going to get a nasty awakening when they realize they're actually building browser apps, and browser apps are really hard to make secure. So that's my general answer, if that makes sense. Cool. All right, well, thanks a lot for coming. Appreciate it. Great questions. And thanks a lot. Hope you enjoyed the conference. I enjoyed it. Thank you.